Hey guys, wanted to talk today about atmospheric science, a little bit of information about the atmosphere and the weather and what's going on and how it all works, and hope that kind of clears up some things. Atmosphere here refers to a thin layer of gas that surrounds the Earth, and you can kind of see that in the picture here. There's the crust of the Earth, and there is a thin layer, even, you know, I don't know, 15, 20 miles up, something like that. It's the upper boundary of what we're kind of talking about here is normal atmosphere. Most of it's made up of nitrogen gas and oxygen gas. Together, that's 99% of everything. Nitrogen is really important for the plant growth. The plants, of course, use carbon dioxide and put off oxygen, and we need the oxygen. The carbon dioxide is an important factor in maintaining the temperature here on Earth. It's a greenhouse gas, so it kind of traps heat in, and this balance is pretty important. We'll talk a little bit more about that. There are some other gases, but 99% or something is up here. A little bit of argon, carbon dioxide. You got some other gases. Depending on where you are on the planet, somewhere between 0 and 4% water vapor. And there's some particulate matters, soot and spores and dust and stuff like that that's mixed in there as well. But it's that layer of gas there. That layer protects us in a whole lot of ways. One, it gives us oxygen to breathe. Two, it keeps us at the right temperature. And three, it actually protects us from ultraviolet radiation and some other things. So there's at least three ways to thank the atmosphere for what it does for us. There are some layers to it here, and you can see that down closest to the Earth is referred to the troposphere. Up above that would be the stratosphere, the mesosphere, the thermosphere, and the exosphere. The main difference between these is the temperature. The temperature is coming and going as this, you can see the numbers here down on the surface of the Earth, room temperatures, something like 20 degrees Celsius. So anywhere from 15 up down to negative 56. It's cooling off as you rise. If you got in a hot air balloon here and rose up, you would get colder and colder. And then through the stratosphere, you would get colder yet. And you can kind of see the picture there as we go up, as the altitude goes up here, then that temperature is falling, moving to the left. Through the stratosphere, tropopause is that region between the troposphere and the stratosphere, but kind of stays steady there. But through the stratosphere, it's going to warm back up a little bit, and then there's a stratopause between the stratosphere and the mesosphere. That stays pretty constant. Temperature is going to go way back down. You can see that in the mesosphere, goes down to about negative 86 degrees Celsius. That's, I don't know what, a couple hundred degrees Fahrenheit below zero, right? So that's pretty chilly. And a little mesopause there between that. The thermosphere, the temperature goes way back up. You can see even here in the thermosphere, negative 86, starting down here, going up to 1200 degrees. And then the exosphere, then that would be, it's really hot up there. Why is it so hot up there? Well, because all that solar radiation is coming in. The light, the heat from the sun is hitting all that. Some of it's being absorbed there. Some of it moves down into the mesosphere and warms here, the stratosphere. And so different layers, it's that solar radiation coming in that keeps kind of everything nice and toasty. This balance is really important. I don't think any of us have been out of the troposphere, really, unless you're an astronaut or something. You're not liable to have ever gotten up here. Weather balloons, and there was a parachutist who took a balloon up into the stratosphere and jumped out and safely landed. But you got to have a rocket or something to get up into the higher altitudes here. So those are kind of the layers. I kind of like to remember tropical silly monkeys throw excrement, but whatever. If you want to keep those straight, then knock yourself out. You can see the distances over here too. Excuse me. This goes up to about 12 to 18 kilometers. That would be something like, I don't know, 8 to 10 miles up, 12, 15 miles up maybe. Not even that high. And then here, 50 kilometers times 0.6 would be about 30 miles up at the top of that. 90 would be 54 miles, somewhere around that ballpark. And it goes on up. The thermosphere, some people stop at the thermosphere. That's what this one kind of does here. But that'd be 480, 500 miles up, something like that. So that's way up there. Remember, too, that the air is also getting thinner as you go up. Air is made up of gas molecules. The gravity pulls those down closer to the Earth, but they have enough energy to kind of move and to go farther out. It's a little bit like steam coming out of a pot on your stove, right? You've got that vapor, that gas form of water, and it's thickest right down there at the stove, and as it kind of gets up higher, it dissipates and mixes in, right? It gets thinner. It's the same thing here. Gravity's holding it down at near the Earth, but it goes all the way up. It just gets a lot thinner as you go up. If you got in a hot air balloon, if you climb a mountain, you can feel that lack of oxygen, that low density air, and so it's hard to breathe if you climb a mountain or go up in an airplane or a balloon or something. Airplanes, sealed, right, like that, but open cockpit airplane. Anyway, lots of fun there. Weather is really important here on the Earth, and there's about 4 factors I'd like to talk to you about that influence how the weather operates and what's really going on there. The first one is solar radiation. That kind of is the most important driving factor of everything on Earth. If we didn't have the sun, we would die. Okay? It would get really, really cold and really, really dark. And so that solar radiation is critical to our life here on Earth. The plants wouldn't grow. There wouldn't be anything to eat. We would all freeze to death. It's just a big deal. It's nice to have a sun. It's nice to be the right distance away from the sun. If we were farther away from the sun, it'd be too cold and we'd die. If we were closer in, it'd be too hot and we would die. We're in this little Goldilocks zone, right at the right place where we get the right amount of solar radiation. Temperature is an important factor. A lot of that comes from solar radiation, but there's some other factors I'd like to tell you about too. The abundance of water. In places where there is more water, that's going to affect the weather, and in places where it's dry, a desert or something, that's going to affect the weather as well. Air pressure is the last one. That's going to kind of push around weather systems, and if you've got high pressure, it could displace a low pressure system, and when the two mix, you get rain and all that. So let's take a little bit of a look into what causes the weather and see how that goes. The first thing we had on our list was solar radiation, and that solar radiation changes over the course of the year. And the main thing that you see here that's causing that is the tilt of the axis. This would represent the North Pole, down here the South Pole of the axis of the Earth. It's like a stick. It's not a stick, but if you put a stick through a globe and spun it, that would be the stick where that it spins about. And you can see that it's tilted over 23 degrees, something like that. There is a line that runs right across the middle of this Earth that we call the equator. They didn't draw it on here. That would have been kind of nice. But everything above the equator we refer to as the northern hemisphere. Everything below the equator is the southern hemisphere. And you can see that while we're having summer, the southern hemisphere is having winter. And then 6 months later, we're over here, and now that axis is tilted away from the sun. The northern hemisphere is tilted away from the sun. We're not getting as much light and heat and solar radiation. You can kind of see in the picture down here how I could have a band of, some rays of solar energy coming in, and if it's hitting in the middle of the Earth, or a part of the Earth that's tilted toward the sun, then all that energy is spread out over a relatively small area. On the other hand, if that same blast of solar energy there hits a little bit higher, where the surface of the Earth is tilted away, out into space here, that solar energy gets spread over a larger area, and if I put the same amount of energy on a bigger area, then each little piece of that area is not getting as much solar energy. That would reduce the solar energy. And so when we're up here in the northern hemisphere and tilted away from the sun, we're not getting as much solar radiation. We're not, it's going to be colder. It's going to be winter, right? Meanwhile, the southern hemisphere is tilted toward the sun, and that would be summer down there. My brother's wife is from Brazil, and he doesn't like cold weather. I'm sorry, he doesn't like hot weather. So when it's summer here, they'll usually fly down to Brazil and visit the family, and then it's spending some winter here, and then he goes down there and it's winter again and stuff. Whatever. I kind of like summer better, but that's him. These we'll see this picture again when we talk about astronomy, but here you can see that the axis is tilted, but the whole face is kind of parallel to the sun there. It's not tilted away from it. It's not tilted towards it. It's kind of just there on the side. So there, everybody's kind of getting the same. They would call that autumn. We would call that spring, as they move from winter around to summer. That would be their spring, and as we move from summer around to winter, that would be our fall. But it's a little more temperate. It's not super hot. It's not super cold. It's just kind of in the middle there. Same thing over here. We'd be doing spring. In the south, they'd be doing autumn. So that's the main thing. Now, honestly, we're a little bit closer to the sun here. The orbit of the Earth around the sun is pretty close to a perfect circle. We have an eccentricity, a number that measures how eccentric or elliptical the orbit of the Earth is. And it's not a perfect circle, but it's pretty close. But we are a little bit closer to the sun in what we call the winter than the summer. And that seems counterintuitive, but it's mostly that tilt and how much that solar radiation is spread out over a larger area that drives that. So that's a big deal there. This picture shows how that energy that comes in, what happens with it. And so here you kind of have to go through a number of possibilities. Here is the sunlight that makes it to the surface of the atmosphere. Obviously, if a ray of sunlight is pointed at Jupiter, it's not going to come into the Earth, right? So of the light that makes it to the top of the atmosphere, some of it, something like 8%, is backscattered. It's reflected off of the atmosphere. 17% is reflected off of clouds. 19% or something like that is absorbed by water vapor, dust, ozone. And again, you remember that picture with the different layers of the atmosphere and how some temperatures were going up and some were going down. And some of that's what's going on here. And as that gets absorbed in different places, that's going to heat up. If it's just passing through, if there's nothing, if there aren't any clouds there or the gases that would hold that, then it's just going to go on through without dropping that heat there, and it would cool off. But you can kind of see the balance. About 46% of the sun's energy that reaches the top of the atmosphere makes it to the ground. This other side over here, some of it is reflected off the surface too. So, but one of that makes it to the ground, whether it be ocean or land, that's going to warm up the Earth, and then that warm Earth moving through relatively cold space is going to radiate heat back out again. So, this is kind of the other side of it. Some of it goes from the Earth into the clouds. Some of it goes in the Earth out to space. The upper atmosphere here is sending that temperature out. This is a little bit like, right now when I'm recording this, we're just moving into winter, October-ish, not quite winter yet, but late fall and mid-fall. And, it's time to put another blanket on, right? Well, the number of blankets that you have on determines how much heat gets trapped in there. And the atmosphere is kind of like that. It's a blanket that holds heat in. If we put too big of a blanket on, then we're going to have too much heat. That's going to hold the heat here on Earth. If we don't have a big enough blanket, then everything runs off and it gets too cold here. So these numbers, seem kind of dumb, whatever, but it's pretty important to our life here on Earth. If things get too cold, then the plants won't grow. If they get too hot, plants won't grow. Certain bacteria grows at a hotter temperature, but not, and so just a lot of variation here. People have been tracking this kind of thing for a long time, and the temperature is an important factor in all of this. So I wanted to talk about this little pattern right here. If you had a radiator and you heated it up, then that radiator gets hot, air bumps up against it, takes that heat, and now the gas is hot, the air is hot. And hot air is less dense. It's going to expand as it heats. That makes it less dense, and it's going to rise. And so that warm air rises, and cool air rushes in to replace that, and then it's heated, and you get this pattern going around. That circular pattern there is referred to as convection. So that's just a natural occurring thing. You see it around cities. My arrows got shifted over to the left somehow, but there's a lot of heat that gets generated here in a city with the cars and the buses and the air conditioners and the lights and the everything that we do discharges energy, and that energy makes heat. And so you can see the little red line here out in the rural area. They've got it down for 85. When you get into the commercial area, it goes up to here to whatever that is, 89 maybe. In the city, though, they're showing that big bump, 92. I've never measured the rural and the urban, downtown, and the difference between the two would be interesting to see. But you could, all that heat's got to go somewhere, and that creates what they refer to as a heat island. There's a little bump of heat right there. Well, that's going to heat the air. The air is going to rise, and cool air is going to rush in, and you can see how cities would have, winds generated by this thermal process here of convection. So that's an interesting thing to kind of think about. Up here, you can see the same thing happening at the ocean. Sunlight comes down during the daytime, warms up the sand. The hot sand warms the air rises, cooler air comes in to replace that, and it gets heated, and there's a convection pattern. At night, it actually goes the other way. When the sun goes behind the earth, then the land is going to cool off, and this water that's been storing up that heat all day is now the relatively warm thing, and so the air above that's going to get heated, and the convection pattern goes the other way. So that's interesting. Right here is a picture of average temperature. They started this back in 1851. We've got data that goes way back past that, but here the last 150, 170 years is illustrated, and there's a trend here, right? We're always looking for trends. We're trying to understand patterns and see what's going on and figure out what that means. Well, they've got it broken down by month, so each year has a slice for each month. I'm not sure why they left a little blank spot there, but you can see that up here you've got more blue than red, and then as you move down through time, it's getting more red and darker red. The scale is here, so you can see what's happening. They averaged from 1851 to 1900 to get kind of a baseline. So basically these first three rows right there, they said, let's take the average temperature over those and just put that there at 0. And then we can, that's where we're kind of basing that from. That's an interesting point in history because that's kind of the beginning of the Industrial Revolution and before all the machines and factories set up and, burning lots of coal to run mills and whatnot, factories and stuff. So kind of going back before the pre-industrial age, that's kind of a baseline. 1900, somewhere around there, a little bit before that it started, but hadn't really had time to get cranked up. We can see that things are changing here. The Earth is warming up. And so the question is that part of a natural process, something larger going on? Is it something we need to be worried about? You hear people talk about climate change, global warming. This is the tip of the iceberg of what they're talking about here. And is this something to be concerned about? Well, in Fahrenheit here, the darkest red, almost black there, is 2.7 degrees Fahrenheit. So, since 1900, or since this average number, 1858 to 1900, it's gone up 2.5 degrees or something. That doesn't sound like a whole lot, Maybe that's not a big deal. What if it keeps going up? Is this the beginning of a trend, or is this something that Earth is going to correct? That's a good question, and we're trying to figure that out. But you can see that there's reason to be alarmed here. There's a number of things that happen when the Earth heats up. One is that ice melts, and we do see the polar ice cap shrinking. We see glaciers melting. We see all of this stuff. That water that melts is going to run into the ocean. That raises the sea level, right? So now Charleston is going to flood, and Florida, and storms. When the ocean has more energy, then we get more hurricanes. When the when the atmosphere heats up and dries out, then we get more wildfires. And so there's everything affects everything else. And so trying to understand this pattern and what's going on is a really important part of the whole thing here. I don't think it's cause for alarm yet, but you can certainly see how it would turn into a nightmare situation. And it's probably past time to start doing something about that. We've made some little efforts, not nearly enough though. It is interesting that this has all come about since the age of industrialization there, and factories and all of the things that we do. Is this a problem that we can fix? If we created it, then we should be able to fix it too. But wanted to show you a couple more graphs here. Carbon dioxide is an important factor in all of this. Carbon dioxide gets released whenever you burn fossil fuels like coal and oil. And so right over here I have a graph of the CO2 concentration. That line represents how much carbon dioxide there is. This is from 1880, so roughly that same time. You can see the carbon dioxide has steadily gone up right there. And the blue and the red line there shows the temperature. So we've gone from degree below the average, 1940, 1950 average, up to about a degree above. There's that 2-degree shift that we've been talking about. And every year, most of them seem to be a little hotter than the last, right? So that's that pattern. Where does that pattern go? Does it come back down or not? The carbon dioxide goes up here into the atmosphere. Again, it's what we call a greenhouse gas. If you've ever stepped into a greenhouse, you know that solar radiation comes in, hits the glass of the greenhouse, and it converts to infrared. It makes heat, and it keeps your tomato plants warm through the winter, right? And you can build a little greenhouse and grow whatever you want pretty much all year, as long as it's warm in there and the sunlight takes care of that. Carbon dioxide does that in the atmosphere. The more carbon dioxide that you have in the atmosphere, then the more it's going to hold on to the heat. It's like putting a heavier blanket on the bed, and it's going to make it warmer here. That's what you're seeing right there. This graph does the same thing, but it goes much farther back. The scale here, instead of going to 1880, this goes 400,000 years back in time. Okay, you get these numbers from ice cores. When you go and drill the ice, you can measure the how much carbon dioxide there was. You can work out how much temperature there was and everything. And the sea level is on here too. So, 400,000 years ago, we had pretty high carbon dioxide. That caused pretty high temperature. That caused the sea level to go up. And then it started going back down, right? And then it went up, and then it went down. And so there's kind of a cyclical nature to that. It's not exactly the same amount of time between peaks on that, but it's reasonable to think, well, this is part of a natural process, and and maybe this whole thing corrects itself. The difference is our carbon dioxide concentration has gone way up here. It's about 30% higher than it's ever been before. And so that peak of carbon dioxide is what concerns people. Again, you're going to get that from burning gasoline and coal and wood, and using any kind of the fossil fuels that we have taken for granted for the last 100 years or something. So it's a tricky question. I'm to me, it's worth thinking about, because there is nowhere else to go. This is our planet. We can't leave Earth. We've sent out, I don't know, 30 people to the moon or something. I mean, it's not like we can decamp and go somewhere else. The moon has no atmosphere, right? So how are we gonna live there? Anywhere else, we haven't gone beyond the moon as a manned thing. We can't get to Mars. We can't. This is it. This is our home, and it makes sense to take care of your home, because there is nowhere else to go. But I'll let you figure out what you think about that. I got something here called the water cycle. I'm sure you saw this back in middle school or somewhere. But you know that there's large bodies of water. The sunlight comes down. A process called evaporation turns that water, liquid water, to vapor, to a gas form. If you put a pot of water on the stove, then you know that water is going to get hot, and it's going to begin to boil and turn into steam. That steam is water vapor. The sun has enough energy to do that. It's not quite the same process, but that evaporation takes water up into the atmosphere, up into the sky here. It stores a lot of it as clouds. It can go from transpiration is another process here, where it can go into the atmosphere. So you've got all this water that's stored up here, mostly in the form of clouds. That can fall down as precipitation. Precipitation could be rain, it could be snow, it could be hail, whatever form of water coming down out of the sky it has. If it's ice and snow, that can get stored in the mountains, right? So that's part of the water cycle as well. It can run into the ground and get stored as groundwater. You may be living on a well, right? Instead of city water, if you live out in the country, you go out and you drill a hole in the ground and you find some groundwater, and you pump that up, and that's the water you drink and use for your house, right? That's groundwater. Groundwater discharge would be like a spring, a natural spring, where water just kind of comes out of the ground. And there's one out not too far from our where we live, and there's springs around. You can find these things. But anything that melts, any of this precipitation that's liquid, like rain or like melted snow or ice, is going to run into streams and creeks and rivers and back into the ocean, and the whole thing starts all over again. And that would be the water cycle. So all of that's an important part of that. That water is an important factor in the weather. Okay? When it's raining, that's part of the weather. When it's dry and it's not raining, that's part of the weather, right? If you get a lot of evaporation but not a lot of precipitation, that makes your home a desert, right? So these are important things to think about. We have to have water to live. Nice to know something about how that works. We can measure how much water is in the air. It's a number called the relative humidity. And basically it just says at a certain temperature, water could hold a certain amount of water, and we've got some fraction of that. And here, maybe at room temperature, you could have 100 units of water, but you've only got 63. This is what it could do. This is what you do have. You divide that, you get 63 right there. Two devices are shown here that are useful for measuring that. This is called a sling psychrometer. It's basically two thermometers, and one has a little sock on it. You get that sock wet, and you spin it around for a little while. Any water on the sock has the opportunity to evaporate into the air. That carries away heat, and the temperature will fall on that. That's called the wet bulb temperature. Meanwhile, the dry bulb temperature, the one that does not have the sock, measures the regular temperature, and that difference between the two, you can work out this number, the relative humidity. Over here you see a digital humidity meter. That's usually what we use these days. I used to have to do this because I did contract work in the textile mills, but then we bought one of these, and that was a whole lot nicer, right? A whole lot easier. When the air has got all the water it can hold, if it can hold 100 units and it's got 100 units, we would say that's 100% humidity, or that the air would be saturated with water. It's completely full, can't hold any more. That's when you're likely to get rain. When it's up close to what it can hold, and then the temperature drops, then it can't hold that much, and it's going to precipitate in some manner, rain, snow, whatever. All right. So humidity is a nice number. You can always find that on the weather report. Relative humidity is 85%, whatever. So that's good. That weather that gets stored in clouds, there's kind of three main types here. You've got the cumulus clouds, those nice, pretty, big, white, fluffy things. Stratus, that's a layer, right? A strata is a layer. So here's kind of layers of clouds, bands of clouds. You've seen that kind of on gray, gloomy days sometimes. The cirrus clouds are the thin, wispy clouds up high. Not a whole lot of moisture stored there, but they're kind of interesting to look at too. These are the three main kinds, but there's a whole lot of variations on these. Here's cirrus clouds. You can see that they're really high up, so there's not a lot of moisture there, and that's why they're so thin and wispy. But you could also have some puffy ones way up high, and those would be cirrocumulus right there. And I've got an altocumulus, high cumulus. So they're not as high as the cirro, but you can see they're much smaller than the down low, the clouds that are down closer to the surface of the earth. There's going to be a lot more moisture there to work with, so the clouds are going to get bigger and fuller and everything. Here's some lenticular clouds. Those are interesting. They look like lenses, and sometimes when there's UFO reports and stuff, the weathermen all chuckle to themselves because they know there's lenticular clouds out there, and people are getting alarmed by it. Stratus clouds down here, the altostratus, the high stratus, the cirrostratus. So there's just a whole lot of variations here, but those three main types kind of cover everything. One more word on here worth seeing is that nimbus. Nimbus refers to rain. So if it's a dark, puffy cloud, it would be a cumulonimbus. That's a big puffy cloud that's about to rain on you, probably some lightning. The nimbostratus would be layers of rain clouds. So kind of look at that. The weather people have all these symbols that they draw to kind of show what's going on, and I think you can see how those would kind of work out. The line is kind of like cirrus, and the puffy thing looks like a puffy cloud, whatever. But that's kind of, you don't need to know those. I just thought I'd put it in there. Lightning has a lot to do with clouds. As the clouds move, they generate static charge. It's kind of like shuffling your feet on a carpet and reaching for the doorknob, and you get that shock, right? It's the same process. The clouds are shuffling past each other, and you're going to get positive charge collected, negative charge collected. Those electrons can jump over here. They're attracted to this positive cloud. So if they pass over a cloud, then you could get cloud-to-cloud lightning, or that electricity could jump to the earth and make a lightning bolt that comes down and hits a tree or something. You need to watch out for lightning, of course. It'll zap the mess out of you. But that's an interesting weather phenomenon right there. Different places get different amounts of rain. Maybe that's not fair. I don't know, but here you see a map of the United States. Right here in South Carolina, it's kind of that teal green. So we're looking at 40 to 50 inches per year of rain. That's a lot of water, right? If you got all that on one day, you'd be up over your waist in water. Meanwhile, out here in Southern California, Nevada, all this desert land out here, West Texas, they're getting a tenth of what we're getting, right? So, you can just see how the precipitation kind of drives what's going on there with how people live. Um, all of this really dry region is pretty dry. Notice this little band right here. That's kind of interesting. There's a range of mountains right here in Washington and Oregon, and wind comes up off of the ocean here, the Pacific Ocean, bringing a lot of moisture with it. As that wind moves up the mountain, it cools, and that cooler air can't hold as much moisture, so it drops it. And it comes down as rain or snow or something. And so one side of the mountain range is up here, even more rain than we get, 60, 70 inches, 80 inches a year. And then the other side of the mountain range is almost a desert. So that's kind of an interesting phenomenon there, and lots of things going on. Right here, of course, is where we grow most of the grain, the corn, the wheat in the country. There's adequate water, and long enough growing season, and everything's right. But so that just kind of shapes how things work. This idea of climates has everything to do with that. If you took the whole Earth and you thought about the incoming solar radiation, and you thought about the temperatures that come from that, and that temperature influences how much water vapor the air can hold, which changes the humidity, which changes the rain and all that, then you get a globe that looks something like that, where here at the equator, they're getting the most sunlight. That's going to be a tropical region. It's hot, it's humid. You got the average temperatures there, and a whole lot of precipitation. You move up a little bit higher, it's dry, and so that's you're not going to get a whole lot of moisture there. It's mostly evaporated, and not a whole lot of precipitation. That's through Texas and Arizona, right through there, that kind of region. We're in the temperate region, the green stuff there. Typically warm and humid summers, check, with thunderstorms, and mild winters. We don't have that bad a winter. You go up to New York, Wisconsin, or something, see the winters they have. That's something else. Now, they would be called continental climate type, right there. Warm to cool summers, very cold winters. The zone can experience snowstorms, strong winds, very cold temperatures. Sometimes it gets below negative 22. I've got a couple kids that live out in eastern Idaho here. They get down to negative 20 fairly regularly, and don't really think a whole lot about it. But, okay, they don't like it, but, it's just part of life there. The polar is extremely cold. That would be up at the poles up here. And the temperature never goes above 50, even in the summertime. So no thanks. I don't care to live there. That would be how it kind of generally works out. But then you've also got the what's going on with the water. And so you can see that it's not just bands like that. It's kind of like that. But here's the tropical region, and then you move up into the temperate, and the dries over. It's a little more. A couple more factors going on, but those climate zones are kind of handy to make generalizations about. Here's the whole Earth, and there aren't any really big surprises here. You can see that green, they put in a couple extra steps and a couple extra, subdivisions on that. But, there's subtropical humid, that's us. Up above that, you've got temperate, that's what we said. The boreal is another name up there for continental. Well, you got continental, which kind of gets divided there, but the polar's up north. Right there, tropical through the middle, but you got desert. There's the Sahara Desert, right? So all of that. Air pressure was the last of those four weather factors, and basically you can have high pressure or low pressure. I've got a weather map over there, and it's marked with H for high pressure, L for low pressure, and then you can see all the weather patterns that are happening, largely because of the high pressure and the low pressure. These little flag looking things, looks like you're at a car dealership, right? You've got all the little banner flags that they string all over the place to get people's attention. These ones, the round ones, represent a warm front. They're also red, so that makes sense. You got warm air that's moving into an area. Front is where you've got a warm air mass that's moving into. That's going to have a lot of moisture with it, and if it meets a cold front, marked off by these blue arrows right there, then that moisture that the warm front has is going to get condensed. It's going to fall as precipitation, rain or snow, what have you. You can have stationary fronts where there's a cold and a warm front, and they're not budging. They're just kind of mashed up against each other. That's going to bring long, week worth of rain, 2 weeks worth of rain or something. And so then finally an occluded front over here would be when there's a cold front that's moving into a warm front, but it's moving faster than the warm front is, so it kind of runs over the top of it. And you've got, they're both moving in the same direction, but that's going to get you dry air. That cold front didn't have the moisture, and the warm front's already moving on out, so it's going to do that. These high pressure and low pressure zones, though, are what drive these fronts. So they kind of steer everything around, and if I've got high pressure here, that's going to push fronts that way, and you can see how all that's going to get influenced by the pressure there. Here's some pressure going on. Here's some hurricane maps. I've always been fascinated by hurricanes, and usually August to November, I'm pretty much glued to the National Hurricane Center online. If you just do a Google search for NHC, that's the National Hurricane Center. It's part of NOAA, the National Oceanographic and Atmospheric Administration, the branch of the government that is charged with measuring and predicting the weather. They have all kind of good stuff on hurricane maps. I'm sure you've seen it. But right here, 2004 was a pretty busy year for hurricanes. You can see all these named storms. NOAA, well, I guess there's a world organization that comes up with the names for every year, but they're alphabetical. So, Bonnie came through, Charlie came through. I don't see D. Sometimes storms get named, but these are just the hurricanes. Didn't quite make it into the hurricane category. You got 5 categories of hurricanes there. You can see they're color-coded. TS is a tropical storm, tropical depression, summer storm, summer depression, and I think this is just wind, and I don't know what all these are. But, you can kind of see the evolution of these things, right? Here, Francis, for example, started out green. It started out a tropical depression, and as it moved across the ocean, it picked up energy, went from a tropical depression to a tropical storm, and then actually became a Category 1 hurricane right there, went to a darker one. Oh, it might be a 3 or something. I'm not really sure on the color. And then it wonked Florida there, just crunched its way. You've seen footage from hurricanes. You know the damage they can do. They bring a lot of ocean water, storm water, storm surge in and flood things real bad. They tear up trees and houses. I've gone on lots of trips to hurricane regions, cutting trees with church groups and patching roofs and doing, stuff trying to help. And it's always interesting to see the damage. It's pretty big, pretty crazy sometimes. But That was one storm. And then right across that, Charlie hit that same little town there. Both of them crossed over that, and this guy came pretty close to it. So um, Florida might not be the best place to live. I'm not sure, but there's a lot of crazy stuff going on down there. Up here, you can see South Carolina got winged a couple times. It was already down to a tropical depression. That's usually what happens. Hurricanes or storms pick up strength as they move across the water, and then when they get on land, they lose that energy. They don't have the heat of the warm water of the ocean, and they encounter all that friction of churning up trees and stuff, and that takes a lot of their energy away, and so they usually drop pretty fast from hurricane status back down into storms and depressions and stuff. But those are interesting to watch and part of this whole weather thing. Again, the temperature matters. The solar radiation is going to warm the water, which is going to give it energy. The what else do we have? The air pressure is going to push that storm one way or the other. And I already forgot what the other one was. But solar radiation, temperature, humidity, the moisture levels and how much water is in the atmosphere right then. All of that's critical to how bad the hurricane is. Tornadoes are also a common thing. I've never gotten to see one of these. Kind of always wanted to. Not too close, you understand, but they look pretty neat and pretty awe-inspiring. It's a funnel of air, much like a hurricane, but it's much smaller, and it's moving across the land. Brings a lot of rain, brings a lot of wind, brings a lot of damage, and this map is showing between 1950 and 1996 how many tornadoes were recorded in each little, I don't know if that's county by county or what, but you can see that Oklahoma is getting it pretty bad here. Florida is getting it pretty bad. So not only did they have the hurricanes, they also got a lot of tornadoes. Hurricanes can spawn tornadoes, and so some of those may be tied up with the hurricanes that were already existed. I don't have information on that, but if you're planning a vacation home, this might be a map to look at. This one and the other one, between the two of them, if you don't like storms. Let me tell you a word about ozone here. Ozone occurs up in the stratosphere, up in that band of the atmosphere above us, above the troposphere. And usually oxygen comes in this flavor. You've got two oxygen atoms that are tied together. If ultraviolet light comes in from the sun, hits it just right, it can give it enough energy to spring out and to separate. Now I've got these individual oxygen atoms. Lightning can also do that in the stratosphere. Those extra oxygen atoms don't like to be alone. They're looking for a deal to make with some other atoms. We'll talk about that with the chemistry stuff. But right here, they can bond on to two others and go to oxygen 3. Normally it travels as oxygen 2, O2, and here O3 is what we call ozone. Now, ozone is nice to have around in the upper atmosphere, not in the lower atmosphere because you can't breathe it. But in the upper atmosphere, it's nice because it blocks ultraviolet radiation. And ultraviolet radiation is a damaging radiation. It's what gives you sunburn. It's what gives you skin cancer. It's what gives you retina damage in your eyes. It's what fades your car paint, your house paint. It's what breaks everything down, right? So this ultraviolet radiation's kind of bad. It's damaging. You can see here in the picture that this band of O3 is stopping most of that ultraviolet radiation. If I didn't have it, then most of it would come on through. Well, we used to use these chemicals called CFCs, a chlorofluorocarbon, and we used them in everything, cleaning products and coolants for air conditioners and refrigerators and freezers, and it was just an industrial chemical that got used all over the place because it didn't have any bad health effects. We tested it on people and it was fine, right? It was cheap to make. It was great. But those CFCs went into the stratosphere, just like all gases do. If you let the coolant out of your air conditioning system, it's going to go into the atmosphere and eventually mix up into the stratosphere. And back 30 years ago, we had a air conditioning coolant called um, Freon that was a CFC, and it had chlorine in it. Well, chlorine will go up there and it will strip away that extra oxygen. So it's no longer the protection from the ultraviolet that it used to be. And those CFCs were pretty bad. We've been measuring ozone layers for a long time. And this is over the South Pole here. And you can see there's a little patch there where there's not hardly any ozone. And that patch got bigger a year later, and a year later it's kind of about the same, but it kept getting bigger, and the darker blue it gets, the less ozone there is. This is referred to as the hole in the ozone layer. And this is bad, right? Because now there's all this ultraviolet streaming in right there. Now, again, this is over the South Pole, so the penguins are getting it pretty hard. Australia is getting a whole lot of skin cancer, a whole lot of radiation damage, ultraviolet radiation damage and stuff. And it'd be easy to go, well, who cares about the penguins, right? Well, I care about the penguins, but this hole in the ozone got worse and worse. I was working in a hardware store in Clemson, South Carolina, in 1992 and 3 when they banned Freon. And they said, guys, we're destroying the ozone. We've got to go to another coolant, and so you couldn't buy it anymore. It just disappeared off of our shelves. Everybody ran and got it because they knew they couldn't get it. And they've changed the coolants a couple times. They've banned other CFCs. Not all countries are doing it. China's not. They're still using CFCs and stuff, but most of the world is going, yeah, this is a problem. And so with that ban, you can see it took a while, but that circle's starting to shrink. It's starting to go less dark blue, and this is a problem that we're kind of fixing. Okay, we created this problem, we recognized the problem, and we did something about it, and we're fixing it here. Okay, it's going to take some time, but we do have an impact on the atmosphere and on the weather and on the ultraviolet that comes in and everything. We have an impact here. This is one we got right. Now, here's another problem that we cause, smog, pollution. Every time you see a car or an old truck that's belching out smoke, that's just pollution. That's just, if people don't know about it, that's one thing. If they don't have the money to fix it, that's, I guess, one thing. But to be a global citizen is to take care of this planet. Again, the only place that we have to go. We have to live here. This smog, this air pollution, causes a whole lot of health problems, and people that have breathing problems are seriously affected by this. I think probably everybody's affected by it. We are putting a lot of chemicals, a lot of hydrocarbons, a lot of bad poisonous gases, carbon monoxide, into the atmosphere every time you turn your car on, basically. Here's a little map of the eastern United States, and it shows the air quality. Just pick out the cities. Right there's Columbia, here's Greenville, Spartanburg, you got Raleigh and Durham. You can just go right on up. Here's New Jersey, a whole lot of industry, a whole lot of pollution going on. New York City, and I guess it'd be more here, wouldn't it? But so I don't know what that is. That would be Connecticut. Boston's right there. The low country South Carolina is green, good air here. I think a lot of that's because of the ocean breeze moving that air. There's not a whole lot of industry in most of that region, so not a whole lot of population. But Charleston would be an exception. But you've also got the ocean breeze that's kind of displacing that air and mixing it, diluting it, if you will, to other places. But this is one of those things that we could do something about. Back in the 70s, Congress had a law that was called the Clean Air Act and Clean Water Act. And, these things were designed to help prevent this. And car industry has been getting better about, we need fewer emissions. We need to start thinking about electric cars. A, the gasoline's going to run out one day, and B, this is what we're doing to our beautiful planet. And again, there's nowhere else to go. So it's something to think about with that. Here's kind of a scoreboard of where we are. This is a hot topic. I'm not trying to make anybody mad or even to preach here, but the carbon dioxide, we're up 419 parts per million. The ice sheets, as the carbon dioxide goes up, the temperature goes up and the ice is going to melt. So that's down 427 billion metric tons per year. We're melting that much ice every year because of this increase in temperature. And that was only with, 2.7 degrees Fahrenheit. That's kind of crazy. The global temperature is up 1.01 degrees since 1880. That's Celsius, okay? Celsius works out to about 2 degrees, 2.5 degrees Fahrenheit. So don't let that fool you. The sea level is up about 4 inches since January 93. That's in my lifetime. The whole ocean has gone up 4 inches since I was, basically finishing up college, right? That's kind of crazy. The Arctic Sea ice minimum extent is down 12.6%. How much ice is there at the poles? The ocean has warmed up, and there's this much extra energy. I don't even know what a zeta. That's a metric prefix, kind of like kilo and milli and stuff. But that's a whole lot of joules. That's a whole lot of energy since 1955. That warmer ocean is going to lead to more hurricanes and stronger hurricanes, and everything just influences everything else. And so you got to be real careful with these things and see what happens. Here are some of the predictions about climate change. These are predictions. Obviously, we don't know what it's going to be in 2100. But if the pattern continues, then the sea level, it's already gone up 4 inches. It could rise anywhere between 1 and 8 feet by 2100. That's going to cause massive flooding. And, Charleston may have to move, right? New Orleans, we saw that back in Katrina, right? It's already underwater. They built dams and levees to hold back the water. But at some point, we can't keep building levees. We're going to have to shut down Charleston and move it somewhere else. Hurricanes become stronger. More droughts and heat waves. We saw that this summer in Europe. They had terrible droughts. They had long wildfires, crazy wildfires going everywhere. California burns all the time. The changes in precipitation patterns. There are places on the planet that are now desert, but they used to be nice forests, right? And climate change has altered the way people live. You don't get to run around and cut down trees anymore. They're all gone. And without those plants taking the carbon dioxide, turning it back into oxygen, that changes the heat balance of the earth, and that changes, everything affects everything else. Right now they're cutting down the forest in the Amazon, the rainforest. That's a big part of cleaning the air and of reclaiming that carbon dioxide, cleaning everything up. They're making some money on it. We've cut down forests before, but we've kind of recognized we need to preserve the forest because they're an integral part of maintaining life here on Earth. The frost-free season, the growing season will lengthen. Well, maybe we can grow more food. Maybe that's not a bad one, but it is a change, right? Global temperatures will continue to rise. The Arctic is very likely to become ice-free. There's no snow at the North Pole, no ice at the North Pole. That would be wild, huh? This is kind of something I'm just throwing in here. Different bacteria live at different temperatures, and there have been some species that have really been hard hit because there's new bacteria that wipe out certain species of animals. And, we just came through the COVID thing. We're not really through it, but we're not at the crisis point we were. And we don't need any more bacteria or viruses that are going to do that kind of thing. So that's a possible climate change result right there. I got a little list of fixes here. There are things that we can do. More important than us would be the businesses and the governments and the bigger organizations. You know, if I throw, I don't litter, but if I throw something out the window, that's just one little piece of trash. Companies do a lot more than that, right? They have the means and the opportunity, and even the motive, the financial gain to dump chemicals, to dump to not be resourceful with their means, with energy and stuff. Um, but if we all work on this together, and if we encourage businesses and governments to be responsible and to take care of our beautiful little planet, then these are some things that could help change all of this and the way and preserve life here on Earth. The more fossil fuel we can keep in the ground, if we're not pumping it up and burning it in our cars, if we have more efficient cars, down here you see sustainable transport, that's what they're talking about. Um, you know, I drive a Honda Fit. If I drove an Escalade, that would be a whole lot more energy that I'm using, a whole lot more heat that I am generating, and in my mind, a whole lot less responsible to waste those things like that. And redesigning how we build our houses to be more efficient, our cars to be more efficient, to waste less fuel, to waste less energy, to leak somewhere in here, insulating your house, right? If you have a well-insulated house, then you don't have to heat it. That means you don't need as big a heat pump, and that means not as many coolant chemicals and stuff. And right here, improving farming. If we can grow crops more efficiently, if we encourage vegan diets, that's going to be a hot topic right there. But it takes a lot of fertilizer to grow food that we then feed to animals so that we can eat animals. And if we kind of cut a couple steps out of that and just ate the plants, then we could save a lot of energy and chemicals and waste there. It's better for the environment because animals emit a lot of methane and you know stuff. It's just things to think about. We live in a certain way and we go, well, it's always been this way. Maybe it's time to change because we're changing the planet and not in a good way. Protecting the oceans, reducing how much you consume. Every time you push a couple buttons and the Amazon truck pulls up, think about how much energy is taken to produce that in China, ship it to California, truck it or train it to South Carolina, put it on a thing, move it around. You got all the waste packaging and if we don't buy something, you got to have things. I understand that, but the levels of consumerism that we live here are unsustainable. And to be sustainable, we need to kind of think about what we're doing and what we're using, and is there a better way to do it that will take care of our planet better. So I'll let you think about that. Thanks for stopping by today. I'm not trying to make anybody mad here, but it's just a good time to think about what we're doing. Thanks. Have a great day.